Before getting into Psylotech's high-resolution sensor technology, I want to talk a little bit about strain gauge load cells. Now, these devices have elements inside, these so-called strain gauges, where there's wires that as you strain the device, wires get a little bit longer and a little bit smaller in diameter, and this change in length and diameter causes a change in resistance, but a very small change in resistance. In fact, only about 0.2% change at the full scale of the sensor. So how do we extract a signal out of such a small change? We have a Wheatstone bridge, which applies across two arms, applies voltage, and then the difference between the two arms, the difference in signal is what is actually amplified and measured. Now, because it's a difference, any noise that gets into one arm or the other arm gets subtracted out in the gain when you're getting the difference. So we're able to extract 500x gain from a typical strain gauge so that we can get 10 volts of output out of the sensor. Now, what's the resolution of a strain gauge load cell? Well, some may say it's infinite resolution, and I suppose technically that is true, but there are other issues besides resolution that affect the sensor, like hysteresis and nonlinearity and drift. And frankly, in my mind, the sensor strain gauge load cell has about 1 part in 2,000 resolution for a very fast response. Now, if there's a little bit of a time lag and time available to do digital signal processing like averaging or digital filtering, you can get probably an order of magnitude better than that. So about 1 part in 20,000 is sort of a safe number for a digitally processed signal coming off of a strain gauge. Psylotech's high-resolution load cell use a capacitive sensor inside of the bridge, and the change in the capacitance as the structure is deformed is much greater than the change in the resistance of a strain gauge. So the result is that the sensor has about 100 times higher sensitivity. Now we have the same instrumentation amplifier architecture, and because there's more signal and a similar signal-to-noise ratio, you're able to get much more gain out of the sensor to be able to see smaller changes in the reading. So for a fast response, these sensors, they can handle about 1 part in 100,000 instead of 1 part in 2,000, and about 1 part in a million with the digital post-processing. Psylotech's high-resolution load cells offer some additional advantages besides just high resolution. For example, alignment, which is critical for under-microscope testing. The fixed crosshead, T-slot grip interface, and the sensing element are all machined to very high precision from a single block of metal. This makes alignment very easy under microscopes and generally speaking. There's also a very high bending rigidity, which is also important for under microscope testing because there may be some grips hanging off of the end of the load cell and gravity can pull down, causing some out-of-plane motion. But because of the high bending rigidity, this really is not an issue at all with these load cells. Finally, there's a very high safety factor on these sensors. And this is done to reduce hysteresis, but it also has the advantage that, especially for a very small capacity load cell, like a 100 Newton load cell, you can have like a 1 Newton range that is very high safety factor. The 1 Newton range of the 100 Newton load cell is effectively 900x safety factor, making them far less fragile, which is a typical problem for small strain gauge load cells. But the high resolution and the high sensitivity introduce a problem because there's better than 16-bit resolution. And also, there's only 10 volts that can be measured. We can't go beyond 10 volts. So how did we address that issue? Each of the high-resolution sensors actually has 2 outputs. One of them is for the full scale, which is essentially comparable to a strain gauge load cell. And the second is a window, which has the much higher resolution. So there's a shifting window within the full scale, and that window can be shifted anywhere within the full scale, either through the software or with a manual knob. It's similar to a microscope where if you want to have better resolution in your image, you go to a higher magnification objective, but you see a smaller overall range. Now, to be clear, the accuracy of the full scale is not necessarily improved. What happens is that the change in the reading is improved. So the change in the reading for a small change over a bigger scale can be improved. So how does the output of these sensors look? Well, here's an example where there's a window and a full scale on a test that was run at 2 nanometers per second for the moving crosshead. So 1.6 kilonewton high resolution load cell, and you can see that the strain gauge, the full scale and the strain gauge load cell, they're pretty similar. You might see a little bit more noise in the strain gauge load cell, but that's really because the only load cell available commercially is a 2.2 kilonewton, and the full scale is only 1.6 kilonewtons. So that means that there's a little bit more noise from that ratio. But ultimately, the full scale you can see is similar to a strain gauge load cell, but the window has less noise in it. There is one limitation that's worth being aware of with the high resolution load cells, and that is that the window in particular can be prone to drift. Now, to partly compensate for that, there's an onboard temperature sensor to monitor the temperature of the sensor body during a test, and in fact one could make a virtual channel that combines both the temperature and the high resolution load cell output to help mitigate this drift. But still, it is ideal if possible to keep the room temperature as constant as you can, and for longer term tests like a creep or a stress relaxation or even a slow rate test, I would say that the resolution would probably need to be downgraded to about 1 part in 200,000. Psylotech's high-resolution load cells are available from 10 kilonewtons down to as low as 10 newtons for the full scale. An axial plus torsion load cell is available, and there is a vacuum compatibility option. The 10 newton load cell uses a smaller T-slot to reduce the moving mass and to improve the resonant frequency of the system. That's me, Alex Arzumanidis, the founder of Psylotech, and I'm calibrating our latest high-resolution load cell for vacuum environment. Just to summarize what I've been talking about today, these sensors have about 100 times higher sensitivity compared to a strain gauge, but they have other advantages. Single sensor, because of this range, they can cover multiple ranges, so you don't have to keep swapping out load cells to do different tests. The alignment is very good because the T-slot, the sensor body, and the sensing element are all machined from a single body. The alignment is excellent. There's a high safety factor, which is particularly useful for small load cells, and there's high bending rigidity, which is good for horizontally mounted samples that are going to be placed especially under a microscope where there's a fear of out-of-plane motion. Thanks for your attention. If you want more information, please contact us at info@psylotech.com.